Hi, ladies and gentlemen. Our last portion of modern physics is going to be talking about the Standard Model. Now, we've previously discussed protons, neutrons, and electrons. And for the longest time, a lot of people thought that these particles were the smallest possible particles in the universe. But the Standard Model talks about the fundamental particles that make up everything else, including the protons, neutrons, and electrons. So Standard Model is really a theory of, I guess you could say, almost everything, but basically of how the fundamental particles interact and form all matter in the universe. This was created in the 1970s. It was really a conglomeration of a lot of different ideas that were put together. This chart on the next page is really a representation of all the ideas in the Standard Model put together, where we have specific groups. We have one group of quarks. We have a specific group of what we call leptons. And over here, we have all these bosons that act as the forces that hold everything together. Weren't really discovered until recently. I mean, the Higgs boson wasn't discovered until last year, in fact, in 2012. Gluons help create the strong force that hold the nucleus together. Photons are really carriers of the electromagnetic field. So anytime there's some sort of electric charge interaction or magnetic field interaction, that's really because of photons. And Z and W bosons, which were only recently discovered within the past 15, 20 years, they create the weak force that govern certain radioactive decay interactions with beta particles. So really today we're just going to go over some basic ideas of what quarks really are, what leptons really are. And you can see that there are 6 types of quarks and there are 6 types of leptons. Now,
there are 2 kinds of quarks that are found in normal matter. Physicists call them flavors of quarks. These quarks are the up quark and the down quark. A proton is formed from 2 up quarks and 1 down quark, while its slightly heavier cousin, the neutron, is formed from 2 down quarks and 1 up quark.
So let's actually write that down for a moment because that's pretty important. A proton is created from 2 up quarks and a down quark, and a neutron is created from 1 up quark and 2 down quarks. Now, as you noted previously on the chart, there are all these types of charge, and we're going to talk about color as well, and how these all work together to create these types of particles.
The red, green, and blue colors of the quarks represent a property that attracts them to one another. It is this color charge property of the quarks that hold them together in a proton or a neutron.
Quarks are really just one type of matter particle and what's interesting about them is that they're always found in groups. And a group of quarks is called the hadron. Okay, and that's where the term Large Hadron Collider comes from. When we talk about those machines in Geneva that accelerate these particles up to near light speeds, and then they collide them together. And each quark always carries a fractional charge. So we take a look at our chart again. Okay, notice that the top, up, charm, and top each carry a charge of plus 2/3. The bottom row, down, strange, and bottom, each carry a charge of negative 1/3. These quarks are grouped in terms of families. Up and down are the most common type, and they're what are found in protons and neutrons. And notice as we get through each family or generation, generation 2 has a larger mass, and generation 3 has an even larger mass than before. The fact is those extremely large masses make them unstable, and they break down very, very quickly, which is why we don't really see them in everyday matter. But through certain collisions, we're able to create these different types of quarks within for the standard model. Now, when we talk about grouping quarks, we already said a group of quarks is called a hadron. Okay, but there are specific types or ways of grouping these quarks. Now, the first rule about grouping quarks that you really have to keep in mind is that the total charge must be a whole number. So keep that in mind. Our main two types of groups are baryons and mesons. A baryon is a group of 3 quarks. So our main example would be the proton and neutron. So with the proton, the quarks that make it up, as we said before, are up, up, and down. That's plus 2/3, plus 2/3, minus 1/3. The total charge is equal to positive 3/3 e, or in other words, plus 1 e, or in other words, 1.6 times 10 to the negative 19. Our neutron example is up, down, down, which is plus 2/3, minus 1/3 e, minus 1/3 e, which is equal to 0 e. In other words, neutrons, as we already know, are electrically neutral. I had previously mentioned color charge, and we know that red, blue, and green were 3 colors. Just keep in mind, this is just a naming convention. There's no light that actually strike these quarks because these are too small for light to reflect off of. It's just the idea that when you take 3 stable quarks and you put them together, red, blue, and green on the color chart, when you combine them together, create white, meaning that white is just a stable combination of quarks. Just like our total charge is also a stable combination of quarks. Which is a quark with an antiquark. Now, normally, of course, it's very unstable to put matter with antimatter, but we're not putting matter with its exact opposite. For example, a pion, it consists of an up quark plus an anti-down quark. So the way we represent it would be with up and anti-down with a bar above it. So the charge of this would be plus 2/3, and since antimatter has the opposite charge, it would be plus 1/3 e, which equals to positive 1e. Okay, which is a whole number, so it fits our rules of keeping a whole number charge. An antipion would simply be an anti-up with a down, which would mean negative 2/3 e minus 1/3 e, which equals to negative 1e. Now, the most interesting thing to note, however, with regards to quarks, is if you actually look at their masses of these quarks are very, very, very tiny. In fact, they're so much tinier than the protons themselves. So when you have a proton made of an up, down, it's going to be much less than the mass of the proton itself in terms of all three combined together. Now, the reason for that is because the mass of the proton is actually mostly consisted of the kinetic energy and potential energies of these particles zipping around, and they collide. And you get that conversion of energy into mass, okay? Which is why the mass of these separate particles are always going to be less than the mass of the actual combined group, or hadron itself. Leptons are the bottom group. We have the electron, muon, and tau. Again, electrons, of course, are very stable molecules, so we see them all the time. Muons and tau, however, are only seen in certain high-energy collisions. And then immediately they'll decay, eventually back down into an electron. What's interesting to note is that during these different decays, you have not only the release of an electron, muon or tau, you have these electron neutrinos, that are released at the same time. And these are actually stable particles. Now, most interesting to note, really, is that leptons are always found by themselves. So whenever we talk about the electron as a fundamental particle, it really is a fundamental particle. That electron can't be broken down into smaller pieces, unlike the proton and the neutron. Okay? Leptons are always found by themselves, which is why they always also have a whole number charge. Of course, that charge would be negative 1e. Unless you're talking about the anti-electron, anti-muon, and anti-tau, which would then, of course, will have a charge of positive 1e. And antimatter is the same as the standard model, it's just that every particle just has its opposite charge. A neutrino is literally as the name sounds. It's a tiny neutral particle. In fact, with the electron neutrino, its mass is so small that we've never actually been able to perfectly measure how tiny it really is. And it wasn't even detected right away because since it is neutral, it doesn't interact with any sort of charge field, and it's able to pass through most objects without being affected because it is a neutral particle.